Welcome back, everyone. We're going to look at the end of the chapter questions in chapter 3, and we're going to do just a few of these questions. We're going to do number 21, which is ranking. Then we're going to do a couple of the math problems 23 and 24, and then end up with 28 if we can. Okay, so first of all, we're to rank the following sets of scenarios. So we're going to do one of these. So we're going to rank from greatest to least, rank them by how much they resist being set into motion. If you remember, a baseball is easier to throw than a bowling ball because a bowling ball has higher mass. So the more mass you have, the more lazy it is. You can think of it as laziness. It doesn't want to change its motion. If it's moving, it doesn't want to stop. That's why it's hard to catch it. And if it's stopped, it doesn't want to move. That's why it's hard to throw it. All right, so if you're wanting the most resistant, that's being how hard they are to resist being set, then it would be the ones with the most mass. So we're looking here, the most mass here would be 15 kilograms of iron. That would be the most mass, that's B. Then 12 is next, that's the next one, A. Then 10 is next, that's C. And then the last is D for 2, BACD. Number 2 says from greatest to least, rank them by weight. Now, weight is not the same as inertia, but it's proportional, right? The more I weigh, the more mass I have. And the more mass I have, the more resistant to change in motion I have. So it would be the same. Which one weighs most? Well, 15 kilograms weighs more than 12, 12 more than 10, 10 more than 2. So it's the same. That's cool. The last one says, from greatest to least, rank them by the support force or the normal force exerted by the table onto them. Well, unless these guys are falling through the table, okay, if the 15 kilograms is falling through the table, then the support force by the table is less than 15. But if it's not falling through the table, then the force is exactly equal to 15. Otherwise, it would be moving. So 15 is being pushed down, that's its weight. And then 15 newtons or whatever, the 150 newtons of support force is pushing up. So this one is going to be pushing down, pushing up equal. This is pushing down, pushing up equal. So if this is equal to this, then it must be ranked the same way as its mass, or otherwise same way as weight. So the one that has the most support force is the one that's pushing down the most. So that would be B, and then A, and then C, and then B. That's the same as before, B, A, C, D. Okay, good. Now let's do some of the math. A woman has a mass of 50 kilograms. Calculate her weight in newtons. All right. Now, newtons weight is in newtons. That's W is weight. And the formula is mg. mg is the mass in kilograms times the acceleration of gravity. And the acceleration of gravity is 9.8 meters per second squared, meaning every time you throw something out of an airplane, it's going to get faster at 10 meters per second every second. Every second, it's going to get 10 meters per second faster. So every second, it's getting faster and faster and faster. So it increases in velocity as it falls. So we can round this to 10. I don't care. So let's say that's 10 meters per second squared. Another way to do it of equal would be that it's 10 newtons for every kilogram. For every kilogram you have, it's 10 newtons of mass. So in 1 kilogram, you're going to get 10 newtons. Well, that's a good conversion because here will be the number of kilograms, then times 10 will give us the newtons of mass. All right, so we have 50, that's her M, and then that's 50 kilograms, and then 10 newtons per kilogram. And so we have a kilogram on top, kilogram on the bottom. They cancel. So I am going to end up with 500 newtons. Okay. Number 24, calculate the newtons of weight of a 2,000 kilogram elephant. Well, again, weight equals mass times gravity. Gravity's 10. So I'm going to have 2,000, that's kilograms, that's the elephant's mass, times 10 newtons per kilogram. That's the acceleration of gravity. I have a kilogram top and bottom. They cancel. My answer is in newtons. 2,000 times 10 is 20,000 newtons. So an elephant would weigh 20,000 newtons. The last here is a bowling ball rolling along a lane gradually slows as it rolls. How would Aristotle interpret the observation, and how would Galileo interpret it? Well, if you remember, Aristotle had this idea. Remember, they didn't do any experiments. The Greeks didn't experiment with anything. They just thought about things and came up with ideas and wrote those ideas and shared them and talked about them. So they were accepted without really any proof that what their ideas were true or not. And so the Greeks, even though they were really bright, had a lot of things wrong because they never proved it to each other, and they just accepted it. So Aristotle had this idea that everything had a natural state, and that objects' natural state was rest. So if you roll a ball or roll a tire or whatever, it's going to eventually go back to its natural state. So it's going to lose velocity until it eventually stops. Okay, so Aristotle said a ball would return to natural, quotes, a natural state, which is rest. Okay, so that it'll just stop. Galileo, remember, experimented. He had marble tracks. He had dozens of marble tracks, and he had tracks of every angle and all kinds of, they were gorgeous. But what he realized was, if it wasn't for the fact that the surface would slow the ball down, it would keep rolling. And if you were to treat the surface and make it slicker, it would go farther. So he knew that there was some force that was slowing it down based upon the two materials interacting, and that's friction. And so he would explain it that the friction is an unbalanced force. Okay? So you have your weight, which is pushing down. You have the support force, which is pushing up. And then you have friction, which is moving opposite of motion. So if the ball is rolling this way, okay, then friction is going to be in the opposite direction. And since it's unbalanced, so friction is an unbalanced force which eventually stops the ball. Okay? And he didn't do that just by, Aristotle was smart, very smart, but he didn't experiment. Galileo, also very smart, he experimented and was able to prove what he said. And we find that it's exactly the truth. Friction force slows down everything. If you can make something slicker and slicker and slicker, you make it more and more efficient. Okay? Just play with a fidget spinner. That's a very, very slick rotation. It's got the cogs in there are just very, very slick, and it can spin for 3 minutes. Pretty cool. All right, thank you.